Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself first. My name is Syahna Khoir with M.Pd. Sari. Imagine the world on the brink of starvation, not because of drought or pestilence, but because of a shortage of a simple element, nitrogen. This was the looming reality in the late 19th century. The world's population was booming. Farmers needed more fertilizer to grow crops. Nitrogen, essential for plant growth, was abundant in the air but frustratingly inaccessible. See, atmospheric nitrogen exists as a very stable molecule, and so plants couldn't use it in this form. They needed nitrogen in a reactive form like ammonia and H2. Limited natural sources of ammonia like guano, bird droppings, simply couldn't meet the rising global demand. The world needed a scientific breakthrough, and fast. Enter Fritz Haber, a brilliant but controversial German chemist. In 1909, Haber achieved what seemed impossible. He found a way to take atmospheric nitrogen, converting it into ammonia. This groundbreaking discovery, known as the Haber process, would change the course of the history. Haber process combined nitrogen and hydrogen gases under extremely high pressure and temperature. He used a metal catalyst like iron to speed up the reaction. The result, a steady stream of ammonia decay ingredient for a synthetic fertilizer. The world now had a way to produce its own nitrogen fertilizer, potentially solving the impending food crisis. While Haber's discovery was revolutionary, producing ammonia in laboratory was one thing. Scaling it up to an industrial level was a completely different challenge. This is where Carl Bose, a brilliant engineer at BASF, stepped in. Bose faced monumental hurdles. The extreme pressures and temperatures required by the Haber process were unheard of in industrial settings at the time. Bose and his team developed new high-pressure reactors, innovative techniques for handling explosive hydrogen gas, and efficient ways to recycle unused reactors. By 1913, the first commercial Haber-Bosch plant was operational, producing ammonia on a scale never seen before. The impossible had become reality. The Haber-Bosch process, at its core, is a dance between nitrogen and hydrogen. Under immense pressure around 200 atmosphere and high temperature around 450 degrees Celsius, those two gases combine to form ammonia. The reaction is presented as M2 plus 3H2 resulting in 2NH3. This equation tells us that one molecule of nitrogen reacts with a 3 molecule of hydrogen to produce 2 molecule of ammonia. The double arrow signifies that the reaction is reversible, meaning ammonia can break down back into nitrogen and hydrogen. This is where the high pressure comes in. High pressure forces the equilibrium towards the formation of ammonia, maximizing the yield. The high temperature, while seemingly counterintuitive, is needed to overcome the activation energy of the reaction, essentially giving the molecules enough energy to react. The interplay of temperature and pressure in the Harber-Bosch process beautifully illustrates a fundamental chemical principle, the Keteler principle. This principle states that if a change in condition is applied to a system at equilibrium, the system will shift in a direction that counteracts the change. In the case of ammonia synthesis, increasing the pressure favors the forward reaction. That is, the formation of ammonia as it reduces the total number of the gas molecule present. However, increasing the temperature favors the reverse reaction, the breakdown of ammonia. as it observes it. The Harber process operates at a carefully calibrated temperature and pressure to optimize ammonia production while minimizing energy consumption. The timing of the Harber process development couldn't have been more critical. World War I had just begun. Germany, blockaded by the Allies, was cut off from its supply of natural nitrates, a crucial ingredient for explosive. The Harber process provided a lifeline. Germany used ammonia produced through the Harber process to manufacture explosives, foraging the world. But the process had a far more significant impact on the world. After the war, the Harber process became instrumental in fertilizer production. This led to a dramatic increase in food production, effectively averting the global food crisis and sustaining the world's growing population. The Harber process is often credited with fueling the green revolution of the 20th century. Synthetic nitrogen fertilizer, made possible by this process, dramatically increased crop yields. Farmers could now grow more food on the same amount of land, improving agricultural productivity and helping to feed a rapidly growing global population. Today, the Harber process is responsible for sustaining nearly half of the world's population. Without it, billions of people would face food scarcity. It's not an exaggeration to say that the Harber process is one of the most significant scientific discoveries in human history. While the Harber process has undoubtedly been a boon for humanity, it's not without its downsides. Moreover, the use of nitrogen fertilizer have led to environmental problems like water pollution and soil degradation. Scientists and engineers are actively researching ways to improve the sustainability of the Harber process. This includes exploring alternative energy sources for the process, developing more efficient catalysts, and engineering crops that can better utilize nitrogen, reducing the need for exercise fertilizer application. The future of feeding the world sustainably will depend on our ability to harness the power of the Harber process while mitigating its environmental impact. That's all the explanation about the Harber process. Nun wal kolonial waste turun. Wassalamualaikum warahmatullahi wabarakatuh.